Okay, everyone, let's start with our next topic then. That is integration. Okay, integration, let's have a look at this. So again, in integration as well, we will just be doing one rule of integration here in paper 1. The other rules are all in paper 3 later. But before we discuss that rule, let's try to understand what integration is about. So integration is basically the opposite of differentiation. You can say this is reverse differentiation. Okay. Integration is reverse differentiation. Okay. So if you do, if you inverse the process of differentiation, that's what integration is. Now, what does that mean? Let's say you have y equals 6x squared. How would you differentiate this? What would we used to do for this? We would say 6 remains as it is, multiply by the power, 6 into 2, that's 12. And the result turns out to be 12x, right? That's how we differentiate functions. But if we had, for instance, dy over dx given, and that was 12 times x, and we needed to find the equation back, the original function back. This process that takes us back from dy over dx to y, this is called integration. So in order to go from y to dy over dx, what we do is we differentiate a function. And then in order to go from dy over dx back to y, we integrate the function. So after integrating, we should get this original function back. So if we have dy over dx equal to 12 times x, the integral of that should turn out to be 6x squared. All right. So that's the idea of integration. It just reverses the process of differentiation. Okay. Now, remember the rule that we had discussed initially for differentiation. What it used to look like? We used to do two things here in differentiation. When you had x raised to the power something, we basically applied these two steps on that. We would say multiply by the power. That's one thing that you would do. And then you would subtract 1 from the power. These were two things, two steps that you used to do to integrate functions, right? So sorry, to differentiate functions, not integrate. So this is how differentiation process used to work. If you had x raised to the power something, we used to say you would multiply by the power and subtract 1 from the power, and that's going to give you the derivative of that function. Now in integration, we're going to reverse that process. How do we reverse that process? In integration, we were multiplying by the power. Sorry, I think I keep saying the other thing. In differentiation, we used to multiply by the power. In integration, to reverse that, we are going to divide by the power. Okay. In differentiation, we used to subtract 1 from the power. In integration, we reverse that. We add 1 to the power. Right. So instead of multiplying by the power, we divide by the power. Instead of subtracting 1, we add 1. Right. That's how integration works. However, we also have to reverse the order in which these two things apply. So think about it. If you start from a point A and you go to a point B, and you pass through these two steps in that process, you follow these two steps in the process, you go from A to this step 1, and then from step 1 to step 1, you go to step 2, and then from step 2, you go to your final destination, that's B. Now, when you're going back from B to A, how would it look like? You would first need to go back to step 2, reverse step 2, and then you go back to step 1, reverse step 1, and then go back to the original function. So when you're going the other way around, when you're doing integration, you reverse this step first, So you say add 1 to the power. Add 1 to the power. That's the first thing you do. Instead of subtracting 1, you add 1. And then once you have added 1 to the power, you need to reverse this step now. You would say divide by the new power. New power means after adding 1, the power that you get after that, you divide by that power. You divide by the new power. So that's how integration works for something like this, where you have x raised to power n. How does this work? Add 1 to the power, divide by the new power. So in mathematical form, we could write it like this. If we had dy over dx, if that was equal to x raised to power n, if the derivative of was of this form, how would we find the original function back from that? By integrating, we would say add 1 to the power. So we have x raised to power n. We would say it becomes x raised to power n plus 1, and then divide by that new power. So divide by n plus 1. That is what the integral of this thing is going to be. So when we integrate this, this is the result that we get at the end. Make sense? Add 1 to the power and divide by that new power. Okay. Now let's apply this process to this function that we saw in the beginning, 12x. So we said the derivative of 6x squared is 12x. How do you go back from 12x to 6x squared? Let's apply that rule now. So we have 12x, the constant, just like in differentiation, the constant that's multiplying, that remains as it is. So 12 remains as it is. It's x raised to power 1. You add 1 to the power. So it becomes 1 plus 1. And then you divide by that new power. So you divide by 1 plus 1. What does that give you? 12x squared over 2. And that simplifies to 6x squared. And you get that original function back that you were looking for, y equals 6x squared. Okay. So this is how this integration process works. Add 1 to the power and divide by that new power. If you have a simple function like this, x raised to power something, this is all that you need to do, these two steps. Make sense? Now there's a notation that you have for integration. So in this case, we were going from dy over dx to y. Now that makes sense. If you have to go from y to dy over dx, you would differentiate. If you have to go from dy over dx, you have to integrate. But sometimes we have to integrate y as well, integrate some expression without having this notation. So there's a notation that we use for integration. Let's try to understand that. But before that, let me remind you the notation for differentiation. What was the notation for differentiation? If you had something like this, d over dx of something, let's say d over dx of 2x cube plus 3. What does that mean? How do you understand this statement? This statement basically means differentiate. What does that correspond to? This d that you've got there. D means differentiate. Okay. Differentiate what? Differentiate this thing. 2x cube plus 3. With respect to x. So x is the variable that this function is defined in terms of. So differentiate this with respect to x. That's the notation that we used to have in differentiation. So if you had, for instance, dy over dx, what did that used to mean? Differentiate y with respect to x. So the same thing here, differentiate y with respect to x. You could say derivative of y with respect to x. That's the notation that we used to use in differentiation. Dx means with respect to x, and the letter d in the numerator, that means differentiate. Okay. Now we have some notation that we will be using for integration as well. So for integration, we have this notation that looks like this. So it's kind of an S, but it's stretched vertically like this to make it something like this. This is the integration sign, integration notation. So if you have something like this notation, and then it says, for instance, 5x squared minus 2, and then you have dx outside. How do you understand the statement? This notation that's here, this basically stands for integration. So you say it means integrate what? Integrate this thing, 5x squared minus 2 dx with respect to x. So x is the variable here. We want to integrate this thing. Integrate 5x squared minus 2 with respect to x. That is what this notation means. So that sign means integrate, and then dx means with respect to x. This is how you would understand the statement. All right, so this is the notation that we will be using for integration. Make sense? So now that we understand what the integration notation is, we can write this rule using that integration notation. And how would it look like? You would say it's integral of x raised to power n with respect to x. What is that going to be equal to? That's going to be x raised to power n plus 1 divided by n plus 1. That is going to be the integral of this thing. Make sense? X raised to power n plus 1 divided by n plus 1. Add 1 to the power, divide by that new power. That's what you get. Now, in differentiation, the result that you used to get from differentiation used to be called derivative, right? The result was the derivative. So after differentiating, the end result used to be called a derivative. Okay. When you integrate something, the process is called integration. When you integrate something, the end result that you get at the end, this is called an integral or integral. That's the result that you get at the end. Okay, so in differentiation, we used to call the result the derivative of the function. In this case, when we integrate something, the end result is called the integral of that function that we have. All right, so this is the integral of this function. X raised to n plus 1 over n plus 1, that's the integral. Okay, so that's the notation that we will be using in integration. Now let's have a look at some examples where this rule could be used. So let's say you have something like this. Integral of 6x raised to power minus 2 with respect to x. You want to integrate this thing. How do you do that? The constant that's multiplying 6, that remains as it is. You add 1 to the power. You have negative 2, add 1 to the power, minus 2 plus 1. Divide by that new power, minus 2 plus 1. Now let's simplify this. What does that give us? 6x raised to power minus 1 divided by minus 1, and that simplifies to minus 6 over x. That's the integral that you get for 6x raised to power minus 2. Is that okay? Any problem with this?
No, sir.
Let's take another example. Let's say we want to integrate minus 5 over 3 x raised to power, let's say 1 over 2 with respect to x. We want to integrate this thing. How do you do that? The constant that's multiplying, that remains as it is. So minus 5 over 3, that will remain as it is. You add 1 to the power, 1 over 2 plus 1, what does that become? That's 3 over 2. And you divide by that new power, you divide by 3 over 2. Okay? And that's it. Now you simplify this. How do you simplify this? There's 2 in the denominator, that's going to go to the numerator. minus 5 multiplied by this 2. What does that become? Minus 10. And then you have this 3 and this 3 multiplying in the denominator. 3 times 3, that's 9 minus 10 over 9 into x raised to the power 3 over 2. That's the integral of this function. Okay, let's take another example. Let's say you have something like this. Integral of 2 over 5 under root x. You want to integrate this. How do you do this? First of all, you would write this in power form, just like we used to do in differentiation. You first need to write this expression in power form such that you have x in the numerator. Instead of the denominator, we want x in the numerator because that's what the rule is for. The rule requires x to be in the numerator, not denominator. So let's bring that x term in the numerator first. What is this going to look like? 2 over 5, when x comes to the numerator, it becomes x raised to power minus 1 over 2. In the denominator, the power was 1 over 2. When it comes to the numerator, the power becomes negative 1 over 2. Now we need to integrate this. We haven't really integrated this yet. Now we need to integrate it. 2 over 5, the constant that remains as it is. Add 1 to the power, so it becomes minus 1 over 2 plus 1, that's 1 over 2. Divide by that new power, 1 over 2, divide by 1 over 2. Now this 2 goes to the numerator, gets multiplied by 2, and you're left with 4 over 5 into x raised to the power 1 over 2. And that's the integral that you get from this function. Make sense? Any issues with this?
No,
Okay.
sir.
Now, something related to the notation that we've discussed. Basically, this number that's multiplying, just like differentiation, since this number does not change, 2 over 5, the number that was multiplying, that remains as it is. As in, the integration process does not do anything to that number. Similarly, minus 5 over 3 here, that remains as it is. It does not change. 6 here, it remains as it is. It does not change. What we can do in general is, if you have any constant multiplying or dividing, you can actually write that outside the integral as well. Okay, if you have some constant multiplying with the whole expression, you can write that outside. Now, let me explain what I mean by that. If you have, for instance, in fact, in this example as well, you could write it like this. You could say it's 2 over 5 into under root x in the denominator. This thing could also be written as 2 over 5 outside into integral of x raised to the power minus 1 over 2 dx. Now, this is something that you will find later simplifies integration in some cases a lot. If you can just write the constant outside, so you don't have to worry about this constant, it just remains as it is. You're just applying the integration process in this thing. All right, so the constant that's multiplying or dividing by the whole thing, you can write that constant outside the integral as well, like this. Okay, and now integrate this thing, it becomes x raised to the power 1 over 2 divided by 1 over 2, and that gives you the same thing, that's 4 over 5 x raised to the power 1 over 2. Now in this case, it does not really make much difference, but you will find later, in a lot of cases, the integration process becomes much simpler if you can do something like this. For instance, if you had to integrate, let's say, x plus 2 over 5 with respect to x. Now, how do you do that? So I'll give you 1 minute to think about this. What do you get from this? What's the integral of this expression? Anyone? How do you integrate this? So take a minute and see what you get from this. Yes, what's the result that you get? Can I have some response?
Sir, 2x square over 10.
Okay. Let me actually simplify this. So basically, you're getting confused at one thing here. We'll do this later. So let me actually just bring this down. After discussing a couple of other examples, we'll come back to this. Let's do this instead. Let's say you have just x over 5. You want to integrate this. How do you integrate this? X over 5? Yeah, so Naima, that makes sense. Yeah, that will be correct. But we'll come to that in a moment. Let's say you just have x over 5. How do you integrate it? One way to think about this could be, you could write this 5 outside the integral, and that makes the process much simpler. You could write this 5 outside so that it becomes 1 over 5 into integral of x with respect to x. Okay, so this constant that's dividing by the whole thing, you could write that outside the integral like this. Okay, and now 1 over 5 remains as it is. What's the integration of x? Add 1 to the power, it becomes x power 1 plus 1, that's 2. Divide by the new power, and that simplifies to x squared over 10. And that's the integral that you get for this expression. So the idea is, if whenever you have something like this, if you have k multiplied by some expression, you want to integrate it with respect to x, you can simplify this integral like this, that you can write that constant outside. Or let me actually do it like this instead. Let's say you have k1 into some expression divided by k2. You have some expression multiplying, some expression dividing. You could write that whole thing outside. You could say this is k1 over k2 into integral of that thing with respect to x. So the constant that's multiplying or dividing, you can just write that outside. K1 and k2 here are constants. So any constant that's multiplying or dividing by the whole thing, you can just pick it up, write it outside the integral, and that simplifies the process a lot. And you will find when we do some more complicated examples, doing this simplifies your integration significantly. All right. Okay. Now, what is the integral of 3 with respect to x? How do you integrate a constant? How do you integrate 3 with respect to x? Any idea?
Sir, it will be x.
Just x? The integration of 3 is x?
Sir, it's the opposite of differentiation. So it would be x.
Is the derivative of x 3?
Sir, it's 1.
It's 1, but here we have 3. Okay, so how do we think about this?
Sir, we can think
Yes,
about it
Hasan?
as 3. We can think about it as 3x power of 0. So then we add
Yes.
1 to 0.
Yes, that's very good. So we could write it as this. We could say 3 is the same thing as 3x raised to power 0. And then we apply the power rule on this. 3 remains as it is. Add 1 to the power. 0 plus 1, that's 1. Divide by the new power. And that gives you 3 times x. All right. So whenever you have to integrate a constant, how do you do that? A constant can be integrated by just putting an x with that, or whatever the variable is. Here we have x. If we are integrating with respect to y, you would put y with that. But you just put the variable here like this. Why? Because in differentiation as well, if you had, for example, 5x, what was the derivative of that? It was just 5. So when we are integrating, we just put x back. All right, that's all that you have to do. Now, this is also using power rule, but since it's used a lot, we would just write it separately as well, that whenever you have to integrate a constant, whenever we have to integrate a constant with respect to x, the result is just going to be k times x. It's just a special case of that power rule, but since it's used a lot, you can kind of just remember this. Integration of a constant that will just add the variable to that constant, right? That variable is going to get multiplied with that, and that's it. That will be the integration. All right, so that's the general rule that we have here. Integration of k is k times x. Okay, and it's coming from the power rule. All right, now let's get back to that example that I showed you there. I have to take this down there as well. Okay, so we've talked about this constant, and now okay, so this rule basically means that if you have constant multiplying or dividing by the whole thing, you can write that constant outside the integral like this. Okay, now this was one example that we did, x over 5 with respect to x. How do we integrate this? We could write 1 over 5 outside, and that makes the integration process a lot simpler. Similarly, now if you had to integrate this thing, the expression that I showed you initially, x plus 2 over 5 with respect to x, this becomes much simpler if you write this 5 outside, right? It's dividing by the whole thing. You can write it outside like this. You can say it's 1 over 5 into integral of x plus 2 with respect to x. Okay, now 1 over 5 outside remains as this. And you just integrate this thing. What's the integral of x? Add 1 to the power, that becomes x squared, divided by the new power, that's x squared over 2. What's the integral of 2? Integration of 2 is just 2 times x. We just discussed that. Now simplify this, that gives you x squared over 10 plus 2x over 5. That's the integral of this function. Okay, x squared over 10 plus 2x over 5. That's the integration. So writing that 5 outside simplifies things a lot. Make sense?
Sir,
Any problem with this? Yes?
sir, why didn't you bring 2 outside as well?
How do you bring 2 outside? We said if something is multiplying or dividing by the whole thing. Is 2 multiplying by anything or dividing by anything?
Sir, it's being divided by 5 too.
No, but only 2 is not being divided by 5. We also have x being divided by 5. So we can't divide 2 by 5 unless we evaluate x plus 2. So first we have to evaluate x plus 2, then we can divide, right?
Okay, sir.
All right. So that's how we integrate this thing. Okay, now let's look at the next rule then. So we've talked about this basic power rule. This is how it looks like. But now sometimes you get functions that are slightly more complicated. Now, just like we had a general power rule of differentiation, we have another power rule of integration. Let's call this the general power rule of integration. Now, what does this look like? Let's say you want to integrate something like this. You want to integrate 2x plus 1 whole raised to power 4 with respect to x. How would you do this now? 2x plus 1 whole raised to power 4. You want to integrate it with respect to x. Now, this does not follow that earlier rule. Earlier, we just said x raised to power n. That becomes x raised to power n plus 1 over n plus 1, right? How do you differentiate this expression? Now, remember how did we use to differentiate such expressions? Let me remind you about that. This was the process that we used for differentiating such expressions. We said we would multiply by the power, right? Subtract 1 from the power. So those two steps would remain as they were. But then we added another step to that. And we said, you also multiply by the derivative of what is inside the power. You multiply by the derivative of the base of the power as well. So whatever is inside the power, you multiply with the derivative of that. So now we also need to reverse that step. Now, let me just copy this here. These are the 3 steps that we have for differentiation, that we used to have for differentiation of such expressions. Right? We used to say multiply by the power, subtract 1 from the power, and then you also multiply by the derivative of what is inside the power, derivative of the base of the power. Okay, these were 3 steps that we had. Just give me a minute. Okay, so this was the process for differentiation. This was the process for differentiation. We used to do these 3 steps. Now in integration, we are just going to reverse these 3 steps. Let's do that. Let's reverse these 3 steps now for integration. Now we already reversed 2 of these steps earlier. We did this for that. We said add 1 to the power and divide by the new power. These were the 2 steps that we already had there. Now we also reverse this last step. Instead of multiplying by the derivative of what is inside the power, now you say divide by the derivative of what is inside the power. So in order to reverse that, now you say divide by the derivative of what is inside the power. So in integration, we have an additional step now. We earlier had add 1 to the power, divide by the new power, but now you also divide by the derivative of what is inside the power, the derivative of the base of the power. You also do that one additional step. Okay. Now you might be thinking, why are we not doing this in the opposite order, as in this was the 3rd step here? Why not have this as the 1st step when we are reversing this? You can have that. This does not make any difference in this case. The 3rd step is just dividing by the derivative of what is inside the power. It's not dependent on the other 2 steps. It doesn't have anything to do with the other 2 steps. So it doesn't matter if you do this first or at the end, it would not matter. The 1st and 2nd steps, they were connected to each other. Why? Because we were supposed to add 1 to the power, and then what we got after adding 1 to the power, we had to divide that by new power. So in that case, the order was important. So in this case, the 1st and 2nd steps, it's important to add 1 to the power first and then divide by the new power. But the 3rd step, that's kind of standalone step, as in it does not really depend on the other 2 steps. It doesn't have anything to do with them. The 3rd step can be done at first or at the end. It does not make any difference. All right. So the order for the first 2 steps is important. For the last one, it does not make much difference. So we could write it like this as well. We could say add 1 to the power, divide by the new power. These were the 2 steps that we used to follow earlier. Now we just have one additional thing, and that's divide by the derivative of what is inside the power. Now let's try doing that here to this integral. Add 1 to the power. What does that become? That becomes 2x plus 1 whole raised to the power 4 plus 1. What's that? 5. Divide by that new power. Divide by 5. Also divide by the derivative of what is inside the power. What's the derivative of 2x plus 1? The derivative of 2x plus 1 is 2. So we also divide by 2. And this simplifies to 2x plus 1 whole raised to the power 5 divided by 10. That's the integral that we get from this. Make sense?
Yes, sir.
All right. Now let's generalize this. Let's write down this rule in terms of in a mathematical form. In fact, we have generalized it already. Let's write it in mathematical form now. So if we have a function like this, ax plus b whole raised to power n, you want to integrate it with respect to x. What is going to be the integration of this thing? It's going to be ax plus b as it is. And you would say add 1 to the power. So it becomes n plus 1. Divide by that new power. You divide by n plus 1. And also divide by the derivative of what is inside the power. What's the derivative of ax plus b? It's a. So you also divide by a. That's the rule that you have for integration now. The derivative of ax plus b whole raised to power n is, integration of ax plus b whole raised to power n is ax plus b whole raised to power n plus 1. That means you add 1 to the power, divide by that new power, you divide by n plus 1, and you also divide by the derivative of the part inside. What's the derivative of ax plus b? It's a, you divide by a. Okay? That's the general power rule of integration. Now notice a difference between this rule and what we had in differentiation. In differentiation, when we wrote this power rule, we wrote it like this. We said, if we have any expression in terms of x, and you had a power on top of that, you would just differentiate it like this. Multiply by the power, subtract 1 from the power, multiply by the derivative of what is inside. In this case, the part inside the power could be anything. There was no condition on that. It could be any expression in terms of x. And as you will find out later in P3, it could be a quadratic function inside. It could be a cos function, sine function, tan function, a log function. It could be anything inside, exponential function, right? So inside this power, you could have anything in differentiation. However, in integration, we have a condition. We are not saying it's some expression in terms of x raised to power n. We are saying it's ax plus b. What that means is the part inside the power, this must be linear. That means it should be an expression with x power 1. You can't have any other power of x here or any other type of function. This power rule will not work in that case. The power rule only works when the part inside the brackets is linear. And you can only integrate functions like this in paper 1 when you have some linear expression inside the brackets raised to power something, then you can apply this power rule. If it's not a linear expression, then you cannot use the power rule. Is that okay? Make sense?
Yes, sir.
Okay, now let's have a look at some examples of this. Let's say you want to integrate 5x plus 1 whole raised to power -3 with respect to x. How would you do this integration? You would say add 1 to the power. So it becomes 5x plus 1 whole raised to power -3 plus 1, that's -2. It's not -4, it's -2, -3 plus 1, that's -2. Divide by that new power. And also divide by the derivative of what is inside. What's the derivative of 5x plus 5x plus 1? That's 5. You divide by 5. And that leaves you with -1/10 into 5x plus 1 whole raised to power -2. That's the integration of this expression. Okay. You could have something else like this. You can have integral of -2/3 into 4x plus 1 whole raised to power 5, let's say. How do you integrate this? This minus 2 over 3, that's a constant. You can write it outside the integral as well if you want. It's going to remain unchanged. So my minus 2 over 3 remains as it is. Add 1 to the power, so it becomes 4x plus 1 whole raised to power 5 plus 1, that's 6. Divide by that new power, and also divide by the derivative of what is inside the brackets, that's 4. Now simplify this. 2 and 2 get cancelled. You have 12 and 3. That's minus 1 over 36 into 4x plus 1 whole raised to power 6. That's the integration of this function. Is that okay? Any confusion? No? Okay, I'll give you a minute to try this now. Okay, we're ending in 5-10 minutes. Okay. Just the last couple of things. Let's say we want to integrate. By the way, I might try starting tomorrow's class slightly earlier. So we generally start at around 2:30, right? So I'll try if I can start it maybe 5-10 minutes earlier, because there is a lot that we still need to cover in this week. So I'll try if I can start a bit earlier maybe. Rijal, can you hear me?
Yes, sir.
Rijal, you had a class on Tuesday from 2 to 3, right? From 2:30
Yes.
to 3 p.m.
Yes,
So
sir.
you said it's only going to be for 2 weeks, so it's no longer going to be the case from next week. Is that correct?
Yes, sir.
Okay, so from next week, if we want, we can have a class at 2:30 as well.
Yes, sir.
Okay, so we might add at least one more class from next week, either on Tuesday or Wednesday. So what we could do is we could probably do Wednesday. Yeah, we could do Wednesday, 2:30 to 3:30, or maybe 2 to 3. Yeah, 2 to 3 maybe on Wednesday. In addition to this class that we have on Tuesday night. All right, so to make it 4 classes from next week. Okay, so keep that in mind. We might have another class added to the schedule from next week. Okay, that will allow us to do more practice. Otherwise, we might not get that much time for practice because we want to end this during Ramadan, before the Eid. So yeah, okay, let's try this. Let's say we want to integrate 5 into 3x squared plus 2 whole squared. We want to integrate this. Take a minute, everyone, and try to integrate this function and see what you get. Let me know what you get from this. 5 into 3x squared plus 2 whole squared. What's the integral of this? Yes, can I have any responses? What is going to be the integration of this thing?
Sir, 5 over 18 into 3x square plus 2 whole raised to power 3. Whole
Okay,
bracket 3, basically.
okay, so let's try this. You're saying 5 remains as it is. That's a constant, right?
That's 5
Add 1 to the power. So it becomes 3x squared plus 2.
whole
You
raised to
get
power
3 here.
3. Yes.
Divide by the new power. And also divide by the derivative of what is inside the brackets. What's that?
6x.
6x. Is that correct?
Yes, sir.
Does everyone agree to this? 5 into 3x squared plus 2 whole raised to power 3 divided by 3 and also divided by 6x. Is this correct? How many of you think it's not correct? So I'll assume the others think it's correct, right? So does anyone think it's not correct?
Sir, because two x terms are being divided. That's why.
So what's the problem with that?
You said that the integral can't be, the equation has to be linear. That's
The
inside
part
the...
inside the bracket has to be linear. Remember this rule? The part inside the power, it has to be linear. If it's not linear, you cannot use the power rule. It does not work here. So this would be wrong. Okay, you can't do it like this. All right, you cannot use power rule on this function like this. And you should also realize that if you do something like this, what are you doing? In the process, you're basically dividing by x. And remember, division by x is a problem in most cases, because what if the value of x is 0, right? You can't divide by x yourself. Okay, and that's what the problem is here. You're dividing by x, that's a problem. X could have a value of 0, so this method does not work here. When you have a linear expression inside, the derivative turns out to be a constant, and you're just dividing by a constant in that case. If you have something non-linear, you'll have to divide by something in terms of x, and that's a problem. Okay, so we can't use power rule here. So how exactly do we integrate this then? If you have to integrate something like this, you'll have to expand it first. Okay, and you do need to know integration of functions like this. It's just that the power rule is not going to work directly on this. What do you do instead? You first expand this function. Now let's try to expand it. We can write the 5 outside, right? That's just a constant multiplying. So it will simplify things if we just write it outside. 5 outside, and inside, what are we left with? 3x plus 2 whole squared. Now, you can treat this as a plus b whole squared. How do you expand that? A squared plus 2ab plus b squared. So 3x squared whole squared, that becomes 9x raised to power 4 plus 2 into 3x squared into 2, that's 12x squared plus 2 squared, that is 4. This is the expansion that you get from this. Okay. And now you can integrate each of these terms separately and see what that gives you. 9x raised to power 4. 9 remains as it is. X power 4, that becomes x power 5 over 5. Plus 12x squared, what's the integral of that? 12x cubed divided by 3. Plus the integral of 4, that's just 4 times x. And what do you end up with? You get 5 into 9x raised 9 over 5 x raised to power 5. Let's just simplify this directly. This 3 and this 12, they're going to get cancelled. We have 4 here. Let's do the multiplication. 5 into 5, 5 and 5, they get cancelled, and you're left with 9x raised to power 5. And then 5 gets multiplied inside. That's 5 into 4, that's 20x cubed, and then 20x. That is the integral that you get for this expression. Make sense? So if you have something that's non-linear inside, this is not linear, what do you do in that case? You'll have to expand it before you can integrate it. In differentiation, there was no condition like this. In integration, we have this condition, and it's really important to remember this condition. Otherwise, you'll struggle a lot in paper 3 later on. This only works if the part inside is linear. Okay, so you need to do this in paper 3 later as well. This condition is extremely important. Otherwise, it creates a lot of confusions. Okay, so this part has to be linear. Otherwise, you can't use this rule. Okay, any question on this? Any quick question? No? All right. Let's just do one more example quickly, and then one more thing after that, and then we end. So let's say we have minus 2 over 3. Minus 2 over 3 into, let's say, 4x minus 2 whole raised to power 1 over 4. You want to integrate this thing. How would you do this? You would first bring this to the numerator. You would say this is minus 2 over 3. In fact, you could write minus 2 over 3 outside the integral, right? That's multiplying and dividing by the whole thing. You can write that outside. And inside, you're just left with 4x minus 2 whole raised to power minus 1 over 4 then. Apply that rule in this. What does that give you? Minus 2 over 3 into 4x minus 2 whole raised to power minus 1 over 4 plus 1. What does that give you? 3 over 4. Divide by this new power. You divide by 3 over 4. Also divide by the derivative of this thing. 4x minus 2, the derivative of that is 4. And that gives you the result. You simplify everything. You have minus 2 over 3 into 4x minus 2 whole raised to power 3 over 4 in the denominator. 4 and 4 get cancelled. And you have 3 left. In fact, you could actually write it like this. 3 times this 3, that's going to give you 9. So you have minus 2 over 9 into this thing. And that's the result. That's the integral that you get from this. Okay. So this is how we integrate functions like these. Last thing now. Some of you might be thinking, no, in fact, I'll not disclose that right now. So let's take another example. Let's say you have something like this. Y equals 3x squared. You have one function like this, and you have another function which is y equals 3x squared plus 5. Then you have another function which is maybe y equals 3x squared minus 8. You have these three functions. If you were to differentiate all of these functions, what's the derivative of the first one? 3x squared, that's 3 into 2, that's 6. 6 times x. The derivative of 3x squared is 6x. What about the derivative of the second expression here, the second function here? What's that? 3x squared, the derivative of that is 6x. Derivative of 5 is 0. So the derivative of this thing is also 6x. What about the derivative of this last function? That is also 6x. All of these functions have the same derivative, which is 6 times x. Right? Now, if I were to give you this derivative, if I were to tell you, we have a function such that dy over dx is equal to 6 times x. And I want you to find y from that. How would you do that? How do you go from dy over dx to y? You have to integrate the function, right? Let's integrate it. 6x squared divided by 2, and that leads you to y equals 3x squared. You're getting this function back, y equals 3x squared. But what if it was this one? That function also has the same derivative, right? So why are we not saying that it's 3x squared plus 5? Why are we not saying that it's 3x squared minus 8? Right? It could be any of those functions, because the derivative of all of those three functions, in fact, many other functions, is 6 times x. We are only getting this thing, right? So what's the problem? The problem is in the function, in the second function and in the third function, we have some constant here that's being added or subtracted. When we differentiate this function, what's the derivative of a constant? It's 0. So whether we have that constant or do not have that constant, the result, the derivative always turns out to be 6 times x, because the derivative of the constant is just 0. So we do not know now, just by looking at the derivative, if there was any constant in that original function as well. Because if there was a constant, it would have disappeared already. When we differentiate it, the constant just disappears. It becomes 0. The derivative becomes 0. So when we are integrating, there is a possibility that there was a constant in the original function as well, right? So for that reason, whenever we integrate, we do something like this with our final result. We say, let's add a constant to that, plus c, because there is a possibility that there was a constant there as well, which we can't see because the derivative of that would just be 0. Okay, this c is called the constant of integration. Whenever we integrate something, we have to write this constant of integration there. Okay, whenever we integrate something, we have to write this constant of integration. So every single time you integrate something, you have a plus c there. Again, why? Because there is a possibility that there was a constant that has disappeared, so you keep that possibility there. So in this case, for instance, the value of c in the first case is 0 because there's no constant, so the value of c in here would be 0. In the second case, the value of c would be 5. In the third case, the value of c would be -8. If you had to find that value of c, they would give you some additional information for that. So for example, they might tell you that there's a point that lies on this curve, let's say 1 and 5. Let's say they tell you that this point lies on the curve. Now, if this point lies on the curve, what you can do is you can just input this point here in place of x, input 1, in place of y, input 5, and find the value of c from that. So in order to find that value of c, you will need some additional information. So generally, it's going to be a point that lies on that function. You would input that point in the function, find the value of c from that. Okay, but if you don't have any point like that, you just write plus c like this, and you always do that whenever you integrate. So now all of these rules that we wrote here, whenever we integrate, we're going to have a plus c there. We have a plus c here, right? So I left some spaces here with all of these rules because we need to have a plus c here, plus c, plus c, and so on with all of these integrals that we wrote. We're going to have plus c's with all of them. Okay, so when we integrate everything, at the end, you write a plus c there. Okay, I hope that makes sense. So that's why whenever we integrate, we will have a plus c there, right? Like this. All right, and that's it for today. This is all that you need to know. Yeah, just give me a minute. This is all that you need to know as far as integrating functions is concerned in paper 1, right? So in the process of integration, for the process of integration, this is all that you need to know. Okay, just the power rule. That's the only thing that you have in paper 1. Everything else you will find in paper 3 later on. The rest of this topic is going to be about applications of integration, right? Now that we know how to integrate functions, where do we use it, right? So one application is going to be, you would have the derivative of a function given. How do you find the equation of the curve back from that? So that's one thing that you can do. We will see how to find areas between graphs and x-axis and graph and y-axis. We'll see how to find volume of revolution. So that's all to come. But for that, this integration rule is something that you will need to use throughout. So now that we know how to integrate, the rest of this topic is about the applications of integration. Just like in differentiation, we had the power rule, and then we learned a number of different applications of differentiation. For example, how to find equations of tangents and normals, stationary points and their nature, increasing and decreasing functions, rate of change, and chain rule. All of them were applications of differentiation. So now that we know how to integrate functions as well, the rest of this topic is going to be about applications. Okay, and that's what we're going to start in our next class, which is not tomorrow, it's actually on Friday. Okay. Rizal, do you have a class tomorrow as well?
Yes, sir.
Okay, you do have a class tomorrow, but you don't have it from next week, right?
Yes, sir.
Okay, so since we want to use this time that you have before our next class now, we might have a class tomorrow night as well. So at not as long as today's class, just maybe 1 hour, so that you have something to work on before the next class. Otherwise, these 3 days will be wasted. So what I'll do is I'll confirm this. I'll confirm this if we can have this class. But keep in mind that we might have a class tomorrow from 10 p.m. to 11 p.m. or 10:15 p.m. to 11:15 p.m. something like that. 1 hour class in which we'll discuss some more concepts of integration. Okay, but I'll confirm that if we have it. Okay. Otherwise, we'll have the next class on Friday. If we can have it tomorrow, I will let you know, inshallah. All right. Yes, Abdullah.
Sir, plus C means y-intercept in this. Like y is equals to 3x squared plus C.
For a polynomial, yes, it represents the y-intercept. But if it was some other kind of function, sometimes in paper 3, you'll see, for example, you have sine x plus c. In that case, it's not necessarily going to be the y-intercept. In this case, it would be, in fact. But if it was, let's say, cos x plus c, then it would not be the y-intercept. It depends on what function you're talking about. It's not always y-intercept. It's y-intercept in case of polynomials only. If you have a polynomial, that means x powers of x power some positive integers, then yes, the c would represent the y-intercept, but not always. Okay.
Okay, sir.
Anything else? Any other questions, anyone?
Sir, if we were integrating an equation, why would we have to add the plus c at the end of the integral? If it's an equation, if it's the equation of a curve instead of a derivative.
So basically, if you have any expression, so if you have x squared plus 2, now integration basically means what expression is x squared plus 2 a derivative of, right? What expression is x squared plus 2 a derivative of? Now, what expression is this a derivative of? You will say x cubed over 3 plus 2x, but then we do not know whether maybe there was a constant or not. There could be a constant, there might not be a constant. We don't know about that. So that's why we put plus c there as well. Right? Because the derivative of this thing is going to be x squared plus 2. That's why that idea of reverse differentiation is important, that integration is just the opposite of differentiation. In differentiation, this constant would disappear. So if we were to integrate this, we would need to consider a constant there always. All right.
So for integration, we assume that every equation is a derivative.
No. As in, I don't understand what you mean by that.
My question was, so if it says that the equation of this line is y equals 2x plus 5, well,
Yeah.
after integration, why would we have to put plus c?
If we have y equals 2x plus 5, if we integrate it, we are saying integrate 2x plus 5 with respect to x, right? Now, what is integration? Integration is reverse differentiation, opposite differentiation. So what expression would have this as the derivative? That's what we're looking for, right? What expression would, when differentiated, give us this thing, right? That's what we're looking for. Now, that gives us 2x squared over 2 plus 5x, but then there could be a constant. We don't know whether there is a constant or not. That's why we put plus c there, because this expression is going to give us 2x plus 5 as the derivative.
Okay, thank you, sir.
So it's just that we think of integration as anti-differentiation, reverse differentiation, antiderivative. So since when differentiating anything, the constant disappears. When we integrate it, we have to have a possibility of a constant being there. It may be there, it may not be there. If it wasn't there, the value of c would turn out to be 0. But we have to consider a possibility of that being there. Okay. All right. Anything else? Okay, so that's it for today. I'll see you again maybe tomorrow or on Friday. In the next class, whenever it is, we will be discussing how to find areas between graphs and x-axis and y-axis in chart. Okay, so that's it for today. Allah Hafiz, everyone. I'll see you again in the next class.
Allah Hafiz, sir.
Allah Hafiz.